Exercise question 4.32 given here, show that for a projectile the angle between the velocity and x-axis as a function is time is given by theta t equal to tan inverse v0y minus gt upon v0x. This we have to prove. For this, in this projectile motion, the object is started from here by making angle theta, this angle theta with the horizontal at time 0. So it is mentioned here theta 0. That means theta is the function of time and it is the time is 0 here. Now the initial velocity is mentioned here v0. The horizontal component of this initial velocity is v0x and the vertical component is v0y. Now come to this point. At this point, this is suppose O and this is point A. At this point you will see the velocity after time t will become vt here and the angle with the horizontal also will become theta t. And the velocity vt is resolved in two components. The horizontal component is the vtx and the vertical component is the vty here. Now we have to prove that here the angle theta t must be equal to tan inverse v0y minus gt upon v0x. To prove this, we'll see here. From here we will draw the triangle that you can see. This is the point A, one more point which is means representing VTX, and we'll draw a perpendicular here. So when we draw the perpendicular, the triangle is look like this. Okay, and here when we are taking this tan theta, this is, you can see that theta t. So if we are taking here tan theta, that means the direction in which the resultant velocity or the velocity will work, that is tan theta, but it is the function of t. So I am just writing tan theta t. That means theta angle with the horizontal is made by the projectile at time t here. Okay, and that must be equal to perpendicular, which is equal to vty. This is equal to vty upon base, this is equal to vtx here. Now we'll see this tan theta t is equal to vty. That means simply you can say this is the vertical component vty in this direction, which we can see that just apply the formula that v is equal to u plus at. So when we apply the formula that v is equal to u plus at, so here this v is actually, this is vty and this initial velocity. So this initial velocity here which we have seen is the v0, and because it is in the vertical component, so we can write v0y. Now you can see at this point A, the acceleration due to gravity will work, and the acceleration due to gravity is minus g. So this will be minus g. In place of A we will write minus g. The time is t here, so the time t as it is we will write. That means the vty can be replaced at v0y minus gt. So it is now v0y minus gt here. Now you can see that the vtx, this vtx is the horizontal component of this velocity at this point A, and we know that in the projectile motion the horizontal velocity is constant because that velocity is the uniform velocity. So it will be equal to the initial velocity, means the horizontal component of initial velocity. So the horizontal component of initial velocity is what it is. This is v0x here. Okay, so these two will be equal here. So in place of vtx we can write now this is v0x. Now you can see that this theta t and this 10 we will take that side, so it will become 10 inverse V0y minus gt upon V0x. This is the same formula that we have calculated for the oblique projectile while calculating the direction of the resultant velocity at any point in the projectile motion. Okay, only the symbols change, otherwise the same formula has derived here. Next question is, show that the projection angle theta 0 for a projectile launched from the origin is given by theta 0 equal to tan inverse 4 hm upon r, where the symbol have usual meaning. Here we have to prove theta 0 is equal to tan inverse 4 hm upon r, where hm is the height, maximum height attained by the projectile, and r is the range here. So already I have made the figure as I explained to you. Okay, and now you will see that the formula for the maximum height, if we'll write maximum height, so it is hm, and this is equal to u square sine square theta upon 2g. Here theta is theta 0, initial angle we are taking, so this is sine square theta 0. Okay, and u square sine square theta 0, here initial velocity, this initial velocity is what? This is actually the vertical component of the initial velocity. So I will write here v0, because here initial velocity is given v0. So I am writing in place of u v0, and in place of sine theta sine square theta 0 here. Okay, so this is the formula for the maximum height. Now look at here for the range. If we'll see, for the range also the formula will be r, and this is equal to v0 square sine 2 theta 0 upon, here it is g. Okay, one more thing that you can see here, in place of u I have written v0, and in place of sine 2 theta I have written sine 2 theta 0 as the symbol given in this projectile motion. Now we'll take the ratio of these two. So hm upon r, this is v0 sine square theta 0 upon 2g upon, this is v0 square sine 2 theta upon g. Now look at here, this is hm upon r, v0 square will be cancelled. Sine square theta 0 we can write as sine theta 0 and multiplication of sine theta 0 upon this. You can see that g and g also would be cancelled, and this 2 will be at the bottom, so this 2 will come at the bottom here. Okay, this 2 is coming at the bottom here, and sine 2 theta, in place of sine 2 theta we can write 2 sine theta 0, this is theta 0, sine theta 0 cos theta 0. So it is hm upon r, this is, you can see that sine theta 0 would be cancelled, 2 2s are 4, and sine theta 0 cos theta 0 would be tan theta 0. So it will come tan theta 0 upon 2 2s are 4. This 4 will transfer this side. So this is 4 hm upon r, and this is tan theta 0. Or simply what you can say, if you transfer this tan here, so you can say that theta 0 is equal to tan inverse 4hm upon r, and this only we have to prove, which we have proven here. We have to prove theta 0 is equal to tan inverse 4hm upon r. Here we have proved theta 0 equal to tan inverse 4hm upon r. This is extra question given here. A projectile has the same range r for the two angle of projection if t1 and t2 be the time of flight in the two cases, then prove that t1 multiplied by t2 equal to 2r upon g. What is given here? A projectile has the same range. When the projectile is having same range, we have learned that for same range the projectile has to projected by angle theta and 90 minus theta. If the projectile is projected by angle theta or by 90 minus theta, then the range will be same. Okay, so we will see that when the projectile is projected by angle theta, the time of flight is given here. It is, we'll write time of flight when projection angle is, when this projection angle is theta. So T1, it is given to us T1. Now you will see that T1 is equal to, here the time of flight, the formula is 2u sine theta upon g. Okay, and for the same range another time of flight is given, and this time of flight is, as we know by our previous knowledge, that this angle should be 90 minus theta. So T2 should be 2u sine 90 minus theta upon g. Okay, so we'll multiply this to T1 multiply by T2. We'll get here 2u sine theta upon g multiply with 2u sine 90 minus theta upon g here. So this is T1, T2, and you can see that we'll write 1, 2 here. This is u into u square, and 2 sine theta, this 2 u into u square, this 2 sine theta, and sine 90 minus theta is cos theta. So here this g and this g I am writing here. T1, T2, I wrote here this g purposely here because we'll change this into the formula of range. So you can see that this is u square. Now 2 sine theta cos theta we can write as sine 2 theta, and this is g, and we know that this formula is equal to the formula of the range. So we can write now 2 upon g, and in place of, since we know that r is equal to u square sine 2 theta upon g, we'll write in place of this r. So it is proven now that T1 multiplied by T2 is equal to 2r upon g, and this only we have to prove.